Welcome to Mr. Vaughn's classroom, where math is made so easy, it's bananas.
Welcome back to Mr. Vaughn's classroom, where math is made easy. Before we get started on today's video, I'd like to ask you to please hit the subscribe button, give this video a thumbs up, and engage with a comment below. In this video, we're looking at Unit 3 on similarity. This is Lesson 11, Splitting Triangle Sides with Dilation, Part 2. Our learning goal in this lesson, let's investigate parallel segments in triangles. We have one learning target in this lesson, and that says I can explain why a segment parallel to one side of a triangle divides the other sides proportionally. There is one glossary term to go with this lesson, and that is similar. One figure is similar to another if there is a sequence of rigid motions and dilations that takes the first figure onto the second. Triangle A prime, B prime, C prime is similar to triangle ABC because a rotation with center B followed by a dilation with center P takes ABC to A prime, B prime, C prime. In other words, the blue triangle is the original. We rotate around point B until we create the red triangle. From there, we dilate using point P as the center, and we turn the red triangle into the green triangle. Notice that the angles stay the same, but the side lengths are growing proportionally. That's what makes them similar. Now that we're done with the introduction, let's go ahead and take a look at the practice problems.
It's all connected, man. The Pythagorean theorem, the Illuminati, my nap schedule. It's all part of a grand design to keep us from the truth.
Practice problem number 1. Segment A prime, B prime, that is this segment that I'm highlighting in blue, is parallel to segment AB. That is this segment that I'm also highlighting in blue. So question 1 wants to know, what is the length of segment AB? So you can pause the video here if you would like to try and solve this on your own. What's important to remember here is dilation. And when we use dilation, the angles stay the same, but the side lengths change proportionately. So what happens is, in order to go from triangle ABC to triangle A prime, B prime, C, we need to multiply each of the original sides by a scaling factor. So first thing I need to do is figure out, what is that scaling factor? Now, in order to find that scaling factor, I'm going to take the new length and I'm going to divide it by the old length. So the only place on here where I get both the old and the new is down here on AC. If I add the 3 and the 6 together, then I find out that the original length AC was 9 units. So now I can take the new length, which is A prime C, and divide that by the original length, which was AC. From the drawing, I can see that A prime C is 6 units. And I just calculated, adding the 3 and the 6 together, that side length AC, the original, was 9. Now, this is not in simplest form. Both 6 and 9 are divisible by 3. So we can do that because anything divided by itself is just 1. So essentially what we're doing is we're multiplying by 1, which leaves it itself, but it'll give us the simplified version. 6 divided by 3 is 2, and 9 divided by 3 is 3. So our scaling factor is going to be 2/3. Now originally, we took that 9 and we multiplied it by 2/3 in order to get 18/3, which is 6. So we can see that this works. Well, now, in order to find AB, I would have taken AB and multiplied it by 2/3, and that would get me A prime B prime, which is 5. So now I need to solve for AB. Well, the opposite of multiplying by 2/3 is dividing by 2/3. So we have AB equals, when I divide 2/3 by 2/3, that just becomes 1 because anything divided by itself is just 1. And then I have 5 divided by 2/3. Well, dividing by a fraction is the same as multiplying by its inverse. So dividing by 2/3 is the same as multiplying by 3/2. Now I multiply across the top. 5 times 3 is 15. I've got a 2 on the bottom, and 15/2 is 7.5. So length AB is 7.5 units. Now we can do number 2. What is the length of segment B prime B? Well, if we look, we would have taken this original side length of BC, and we would have multiplied that by the scaling factor, 2/3, and that would have given us B prime C, which they have labeled as 7. So now we need to solve for BC. The opposite of multiplying by 2/3 is dividing by 2/3. And whatever I do to one side, I got to make sure I do it to both sides. Well, on the left, anything divided by itself is 1. So we have BC. And now 7 divided by 2/3. If I divide by a fraction, it's the same as multiplying by its inverse. So that becomes 7 times 3/2. 7 times 3 is 21. And 21 divided by 2 is 10.5. So the original full length is 10.5. But what we want is the little missing piece between B and B prime. So B prime is going to equal the original length, 10.5, minus the new length of 7, and that's going to be 3.5. So this little missing segment in here is 3.5. I hope my way of explaining this makes sense to you, but if you do still have any questions, please feel free to leave a comment below.
Let's turn up the heat on this equation. A little bit of multiplication here, a pinch of division there, and voila!
Practice problem number 2. Explain how you know that segment DE is not parallel to segment BC. So we are talking about DE and BC. So if these are parallel, then I should be able to dilate this using A as my center, and the sides should be proportional. So let's find our scaling factor. If I take AB and I multiply it by a scaling factor, then I should get AD. So if I want the scaling factor, then that is AD divided by AB. We can see that AD is 4, and we can see that AB, when I add these together, is 6. Now that's not in simplest form, because 4 and 6 are both divisible by 2. And I'm allowed to do this because anything divided by itself is 1, so this is really the equivalent of dividing by 1, which doesn't change anything. So 4 divided by 2 is 2, and 6 divided by 2 is 3. So my scaling factor is 2/3. Now, if these two lines in blue are actually parallel, then I should be able to take the original side on the bottom, AC. I should be able to multiply that by this same scaling factor, 2/3, and I should get the new AE. Well, AC, I can see that by adding 9 and 15, I get 14. So 14 times 2/3 would need to equal AE, which they've labeled as 9. Well, 14 times 2 is 28. So I have 28/3 on one side and 9 on the other. 28/3 is 9 and 1/3. 9 and 1/3 does not equal 9, because this is not true, these are not parallel. Parallel lines cut triangles proportionally. These are not proportional. Therefore, they are not parallel. So that is how we can prove it. I hope this way of explaining it to you has made sense. If you do still have any questions, though, please feel free to leave a comment below.
Here we go, folks. We've got a real barn burner of a math problem on our hands today. Let's see how this equation plays out.
Practice problem number 3. In right triangle ABC, side AC equals 4 and side BC equals 5. A new triangle DEC is formed by connecting the midpoints of AC and BC. What is the area of triangle ABC? So the first thing you need to understand is the area of a triangle is 1/2 base times height. So for number 1, we have a base of 5. So 1/2 times 5 times a height of 4. 5 times 4 is 20. And 1/2 of 20 is 10. So the area of triangle ABC is 10. Now, number 2, what is the area of triangle DEC? And if you want to pause the video to try it by yourself, please feel free to do so now. Now let's look at number 2 together. We know that they connected the midpoints. Well, midpoints divide in half. So if the full height was 4, then half of that is 2. And if the full base was 5, then half of that is 2.5. Now we have 1/2 times the base, which is 2.5, times the height, which is 2. 2.5 times 2 is 5. And half of 5 is 2.5. So this is the area of triangle DEC. And now the last part, does the scale factor for the side lengths apply to the area as well? Well, the scale factor for the side lengths we went from a scale factor of 4, or a side length of 4 to a side length of 2. So new length of 2 divided by old length of 4 is the same as 1/2, because 2 and 4 are both divisible by 2. But when we look at the scale factor of area, we have a new area of 2.5 divided by an old or original area of 10. These are both divisible by 2.5. That makes it a scale factor of 1/4. So the answer would be no. The side scale factor was 1/2, but the area scale factor was 1/4. So hopefully everything I've explained and shown in these practice problems has made sense to you. But if you do still have any questions, please feel free to leave a comment below. Now let's go ahead and review the learning target for this lesson one last time before we end the video. So we did have one learning target in this lesson, and that said I can explain why a segment parallel to one side of a triangle divides the other sides proportionally. And I hope you see now that this is just a big fancy way of talking about dilation. If the lines are parallel, then the opposite corner is our center, and we're dilating towards that point. And so what we're really doing is we are shortening the sides through dilation. And in that case, it's going to be proportional. With similarity, the angles stay the same. The side lengths are adjusted proportional by the scale factor. Now, if you found this helpful, in the bottom left, you'll see another video of mine that YouTube thinks you'll want to watch. In the bottom right, you'll see the subscription button. It would really help the channel out if you would subscribe. Please give this video a thumbs up. If you have any questions or comments, please leave a comment below. I read them all. And if you would like any one-on-one tutoring, I'm going to link my SuperProf and Wyzant accounts in the description. Please feel free to check that out, and I would love to help you out one-on-one. As always, I look forward to seeing you in the next lesson.